So milestone 4, you will be implementing a traveling salesman problem. This problem is empty hard. So you're given many depots. Some of them are pickups, some of them are drop-offs. For each package, you'll have to first pick it up from one depot and drop it off at another. You will need to find the fastest delivery route. This problem can be divided into, first, you'll need to estimate the travel time between all of the locations, all of the depots of interest. You will need to then find a good delivery ordering. And finally, return the final tour. Finding a good delivery or ordering can be done with a lot of algorithms covered in lectures. So I will not be covering those in this tutorial. What I will be covering is the first part, estimating the travel time between all locations. And also multi-threading. You'll have to do all of these in less than 50 seconds. So it's very important for you to organize your time, your compute time. Estimating the travel times. What we recommend is you to pre-compute the travel times and store them in some sort of data structure like a matrix. So from the from and to intersections, you can directly get the travel time in one time. We have a few options. The first option, which is the fastest one, is to estimate by Euclidean distance. This is fast, but very inaccurate because this case is not accounting for any path, any speed requirement, any turn penalties, nothing. Option 2 is to get the exact path. It's accurate, but slow. So the most naive implementation of computing the travel time matrix is to use A star to compute from all of the sources to all of the destinations. Assuming we have K depots and V total intersections, can anyone tell me what is the complexity of this code? So we have K sources and destinations, and we have V total intersections. What is the complexity? What's the complexity of A star? Does anyone still remember Dijkstra? You will probably be asked about the complexity of A star in your OP2. So the complexity of A star is V log V. Then what is the total complexity of this? Yeah. K times V times log V. You sure it's V squared or K squared? Yeah. O of K squared V log V. The K squared comes from the nested for loop. But on large cases where K is larger than 300 intersections, this can be very, very slow. And that will limit time for your later ordering optimization, which should take more time. So our next option which requires a bit more thinking, is to use the multi-destination Dijkstra. As you should already know, the time it takes for Dijkstra to find the path to one single destination is the same for Dijkstra to find the path to all of the destinations. So running one multi-destination Dijkstra takes the same time as A star. So what is the complexity for this? So we're looping only for the sources, and in each time we are calling multi-destination Dijkstra. So that will compute the path from the source to all of the destinations. So what is the complexity? KV log B. We got rid of the K squared. So it's KV log B now. After we get this algorithmic improvement, if we want even more speed, we can start using parallel programming. This is just a graph to motivate parallel programming. By Moore's law, the number of transistors on chip increases by year, and that's shown by this magenta line. It increases by year, but single-threaded performance hits a threshold and it becomes lower by year. The frequency, this is the clock frequency on chip. It also hits the threshold and starts decreasing. Typical power is slightly increasing by year. This is something we don't want. So in order to make use of the increase in transistors, what the developers figure out is that they can increase the number of cores on each of the CPUs. So that's where multi-threading comes in. We can have multiple cores. This is an example of a 4-core processor. We have 4 cores. Each core has its own processing unit, its own cache, and all 4 cores communicate to a shared memory space. Each core can execute its own instructions. All cores share common memory space. And applications with a single thread that doesn't use multi-thread at all, just has 1 core running and talking to the shared memory. All 3 cores are idle. Most applications use 1 thread. You have been taught to write only single-threaded applications. Single-threaded applications do not need to worry about sharing memory because it has the entire memory space to itself. But if you need to add more cores, more threads, you'll need to worry about shared memory. Because multiple threads could modify the same variable. They can read the same variable. And if some other cores are writing the same variable that's not expected by another thread, it can cause problems. So let's look at what is behind the scene for multi-threaded programs. In a single-threaded program, we have in our core, we have the PC program counter that is a pointer that points to somewhere in the instructions in memory, which you should already know from 243. You have a stack pointer that is a pointer that points to the stack position in the stack. The memory starts from 0 Then it has the instructions or code that's translated into assembly, then instructions. It has then the global variables allocated here. Then it has those heap variables that is dynamically growing downwards. At the end, it has the stack that starts at all F's and it grows upwards for local variables. Is it good for a single-threaded program? You should already be very familiar with this. A multi-threaded program has 2 cores. Each of the cores also has its own program counter that can point to somewhere in the shared instruction set, instruction memory. It has separate stacks. So the stack pointers are only pointing to its own stack. The stacks are not interfering with each other. So thread 1, thread 2, the global variables, heap variables, are all shared by all of the threads. Each thread gets its own local variables. So thread basics, just repeating, each thread has its own program counter. So it can be executing a different function and is almost always executing a different instruction from other threads, or it could be executing a same instruction as other threads that could cause problems. Each thread has its own stack. It has its own copy of local variables. Each thread sees the same global variables and the dynamically allocated memories. So each of the thread that has a pointer to it can read and write dynamically allocated memory. This implies the threads can communicate effectively through memory if you design it in a proper way, because all of them can see the global variables and the dynamically allocated memory. So you can achieve very fast communication. But you must be careful that the threads are not conflicting in reads or writes to the same memory. If the 2 threads are all writing to the same global variable at the same time, then there's no guarantee which one can win. So that may cause memory corruptions, unexpected behavior, and seg faults. You can have more threads than CPUs, and I'll show you that afterwards. If you have more threads than CPUs, that means your cores have fixed resources, but you can have more threads running on a single core, sharing the same resources. So if one resource has to be shared and it's taken, the other thread must wait for it to be freed. The multi-threading libraries you may use, you have 2 options. The first option is the OpenMP. So at program start, when your main starts executing, it starts at the first main thread. And then if you want to multi-thread a for loop, you can use OpenMP Pragma OMP parallel for. This is a compiler directive that can compile, and if your compiler doesn't support OpenMP, it will just run the for loop like any single-threaded program. If it does support OpenMP, it will detect the number of cores, the number of threads your current machine has, and then it will divide your for loop accordingly. This is all done automatically. Then if you want to have more control over your threads, you can use the C++11 threads library. And in this case, you will need to manually define the functions your threads are executing, manually call thread to execute your functions, and manually call join. In this tutorial, I will only be showing the OpenMP approach. So say you have a for loop like this. The only thing you need to do is to add the pragma OMP parallel for command above it. Then the compiler will automatically detect the number of cores on chip. And if this is a 4-core CPU, it will divide the 100 into 4 chunks, continuous chunks for each thread to execute. Then after all of them finish executing, it will join back to the main thread and complete the following code. So let's do a simple demo to show this. So we want to do the OpenMP back. First, look at the code. So we're including omp.h, that's a header file for OpenMP. Then what we're doing is we're defining a vector length of 1000. We are defining 3 vectors, A, B, and C, of vector length. We're initializing randomly, not randomly, we're initializing AI to I, BI to I mod 50 plus 1. We don't have to care about that. Then we have a timer that times the second for loop where we are doing some computation on A and B and storing into C. Let's first get the timing for without parallel for. So we're commenting out the pragma OMP parallel for. Let's make and time. So that's the time for executing with single thread. And oh yeah, let me show you how to get the information on the number of threads you can use. LS CPU. LS CPU. LS CPU is the command to output all of the informations on CPU. And we can see we have 16 threads, 8 cores, and 2 threads per core. And that means we are using an 8-core CPU that can hyperthread 2 threads per core. Two-way hyperthreaded CPU. And yeah, let me get the timing data first, and then I'll enable multi-threading. Can anyone make a hypothesis on what will happen with this?
It's a lot faster.
It will just be faster. We make It got a lot slower. Any idea why? Let's disable this command and see if it helps. Still slower. And we do have 16 threads. And that is because our problem size vector length of 1000 is too small. Because making threads also take time. Let's increase this number to, I added 4 zeros. And let's test it. So that is multi-threaded times. Then let me disable parallelization. We are getting a speed up. Let's see how much speed up that is. Calculator. We went from 0.062411 to 0.00831,714. 7.5x speed up. That's how you compute speed up. And let's do it again by adding 2 more zeros and see if we can get even more. Remember, we have 16 threads. So in theory, we should have 16x speed up. So this is single threaded. We have 6.2399 over 2.752197. No. So our timing is obviously affected by the machine load because this is not a light-weighted machine right now, but it's around 8x speed up. Why are we not getting 16x? Yep. But the time it takes to make the thread is amortized by the problem size already. Yes. Yes. Because we have 8 physical cores, we have 2 hyper threads per core, the two hyperthreads per core is sharing resources on a single core. And in the operations we're doing, we have dividers. We need to use multiplier and dividers. We only have one divider on a single core. So the two cores must make context switches to wait for each other. So the true multi-threading we're getting is only on the 8 physical cores. So we're limited by the 8 physical cores. So these are from measurements made on a zero-weighted machine. So with a problem size of 1,000, we are getting a 0.25x speed up. So that's a 4x slowdown. For 100,000, we are getting a 0.68x. And this is how it's starting to amortize out the overhead for creating threads. Afterwards, we are almost fixed at 7.6x speed up. So the idea is we need enough work to amortize the overhead for making threads. So only parallelize when the problem size is big enough, because parallelization can slow you down. The syntax to convert to use multiple threads is simply include OMP, .h, then pragma OMP parallel for all of the for loops. For all of the variables that are declared before the for loops, these are treated like global variables that are shared by all threads, even if they are local variables inside main. Yeah. But I didn't get that. For syntax wise, you are free to do anything. You just have to make sure the logic makes sense. If your for loop is dependent on A, then you'll need to be sure that no other threads are modifying A at the same time in a way that you don't want to.
For example, A is like the sum of the element like A of I equal to A of I minus 1 plus A of I minus 2, then like it's like that, it's like depending on like the value. So
that is a good point. If you are making A of I dependent on some of the previous indices, this will not work because you are not guaranteed that the multi-threading are doing it in correct order. So you don't know of the order.
But doing something like that would then like compile undefined.
You will just get weird results. I'll show you that later. So local variables like I that are declared within the for loop are all local variables that are separate per thread. So that's local per thread. Let's consider this program. we are setting AI in a parallel 4. Then we are printing AI in a parallel 4. What will the program output be? Let's demonstrate that with a typing speed contest. Can I get 2 volunteers? So what will happen is that I will add an extended keyboard to this computer. I will open up the text editor. Okay, let me move it over. So I want someone on the external keyboard to type on line 1, and someone use the laptop's keyboard to type on line 2. And whoever gets the line, I am an amazing electrical and computer engineering student because I am a great typist and programming is mostly about typing speed, on their own line wins. There's no prize. We normally hand out chocolate bars, but we don't this year. What? Okay, who wants line 1? Who wants line 2?
Right.
Are you gonna go take the second one or? I'm not gonna.
It's over. I don't even know what I'm typing.
Do I just type? Or is it set up already?
It's set up already. You just have to make sure you're ready.
Okay.
3, 2, 1, go.
Wait, what?
Type on your own line. You have line 1 and 2. Type on your own line.
Oh, wait, which? No, we have to fight over it? No. No. Hey.
Okay, no backspacing from now.
Oh, hey. No. Won't let you. I don't think anyone will win. No way. I'm not even doing anything anymore. I'll let him type it out. No, wait, what? No, wait, there. I'm trying to. I can't copy it. There, now it's on line 1. No. Yeah, congratulations.
Congratulations. That is a very good demonstration of multi-threading. two threads are trying to fight over the control for typing, for printing. And one thread can only successively complete typing if the other thread gives up. So let's see the demo for printing. That could give you some thoughts on what will happen if two threads are trying to print together. And let's see the print demo. So AI is set here. So we know that A is initialized to 50, B is initialized to 2, and then A is set to AI plus BI, which is 52 in the first for loop. Then in the second for loop, we are doing OMP parallel 4 to see out AI. Let's make and see what happens. Does this look familiar? So this is what usually happens if printing is not controlled and all of the threads are trying to print at once. So this is how one thread can print when another thread is printing. Very similar to the typing contest. So what we need to do in this case is that we need to ensure that at one time only one thread is printing. So we can use this pragma OMP critical to define critical sections. This will tell the compiler that this section within this bracket is critical. So all of the threads need to wait for other threads to finish this line, this section, before they start grabbing this section. So let's save. After this, we see that printing is back to normal now. But this is not in order, which makes sense because it's multi-threaded. And just to show you that without multi-threading it works, that was actually because of multi-threading. I'll disable multi-threading and we can see the printing in order. So that is the critical section. Serialize where needed. OMP parallel 4 runs different loop iterations on different cores in parallel, and this does not check if any of the state is safe or correct to execute. So it will just randomly give you whatever it gets. So to do any of the error checking, if needed, you can use this pragma OMP critical to ensure that only one thread at a time can execute this block. And blocks are defined by the brackets. But making everything critical will destroy your performance because you're making it serial again. So you're not gaining anything from multi-threading. Let's move on to pathfinding. These are the calculations we took, the measurements we took for n equals to 175, d equals to 20. For k is 370 interesting intersections. We are getting iterative A star, which is the k square v log v case. It takes 1,280 seconds. And we set this as the baseline. If we only parallelize this, we get 7.6x by parallelism because we have 8 cores. Then if we move your algorithm to multi-target, multi-destination Dijkstra, we are getting a 33x speedup by algorithm itself. Then we parallelize the multi-destination Dijkstra. This in total achieved a 250x speedup by algorithm plus parallelism. So our recommendation is always tune your algorithms before applying parallelization. So parallelization should be the last step. After all of the algorithm tuning, we want to add parallelization to this code. Remember, this is just the range base 4 shorthand for going from I equals to 0 to t intersections of sides. What we need to do is to add the pragma OMP parallel 4 before this for loop. And inside this for loop, we are calling find paths, which is the function to call multi-destination Dijkstra, and returning the path. Can anyone tell me, will this code work? Previously, it works with single thread. So this will make 16 threads to wrong find path. Yeah. And why? Wavefront is shared. Yeah. We don't want the shared globals to be modified at once. And especially wavefront is very important for your Dijkstra algorithm. And if multiple threads are messing with it, it will destroy your solution. So what we want is we want to move the wavefront into find paths to make it a local variable for find path, because each rung of Dijkstra needs a single wavefront. And that's called privatized variable. And then inside each of the threads, it only modifies its own private copy. What about that variable, key intersects? Do we need to worry about privatizing that one? And why not? Yes, because we're only reading it. If we can guarantee that we are only reading in multiple threads, but not writing to it, it's fine. Now, if these variables are local variables of this function, is it okay to keep them like this? Our pragma OMP parallel 4 is here. And these variables are local variables of this function. Is it okay to keep them like this? Yeah.
Of nine. The seven, then nine, like.
Yeah.
inside that.
Yeah. At the scope of this for loop, these two variables are still global. So we have to privatize those as well. Let's go to the demo. We use the golden solution and you make release. And I'll call ECE297 exercise 4 -- run tester easy Toronto. Just to show you. So easy Toronto uses the case where we have 25 deliveries and 2 depots. So we have 0.7192 seconds. Yeah. Go to the code and 4. In find all paths empty, we are enabling multi-threading of the multiple destination Dijkstra. So 0.7 seconds is for parallelized multi-destination Dijkstra. Let's disable that and do the timing again. (4.88516 seconds. That's also about 7.6 seconds. Now, next I will be I'll re-enable the parallelization again, and I will be explicitly adding in bugs to break our parallelization. Define. So if I define this variable, I will be making this vector global. And let's see what happens. This falls back to the question where you ask how do you debug it. So in this case, you will see something like double free or corruption. But this doesn't tell you anything. So the first thing to check if you get something weird like this is to disable your parallelization and see if it works. So it passed. Whenever you see something weird happen and you have parallelization turned off, always turn off your parallelization. And if it passes this way, then it's because of some variable being global. Let me enable parallelization again. How to check something like this? So we were getting a crash. So whenever you get a crash, the best way is to do debug tester and open the debugger. So I already set the unit test debug configuration. The build target to be test libstreet map, launch target to be test libstreet map, and I'll do the build. And I will open the debugger without setting any breakpoints and wait for it to crash. So it just crashed. Then I'll look at the call stack. So we have 16 threads, 16 stacks, and it has one thread that has paused on exception. I'll go into there and I'll scroll to where it crashed. It's here. So we are trying to resize all nodes. All nodes is actually the variable that we just made global. So with something like this, it helps you locate which variable that is causing issue right here. So all nodes. So what we need to do is just to make all nodes private to all of the threads. And let's do the same thing for the priority queue again. Just to show you that we have different ways of crashing or failing. Make release. Run tester. So in this case, what it returned is path was empty. So path is not legal. Failure. So it actually exits smoothly, but it's giving a path is not legal. Path it was empty. Failure. And that is because multiple threads are modifying the same priority queue, which is not expected for each thread. And you may also get other errors like in previous years we got for the priority queue error, we get the program is stuck in some infinite loop and a lot of other stuff. If the program gets stuck in some infinite loop, then the debugger is also a good technique for you to look at. So in that case, you can just open the debugger, and if it's stuck somewhere, you just pause and see where it gets stuck. And yeah, because it's not coming up for us, I think. So I can't really show you. But you get the idea, right? Yeah, it's keep failing in is legal. So now, after we do all of the computations, we want to store everything into a matrix-like data structure. Say we can make it into a vector of paths. So what it will look like is we get it from the from intersection ID, depot ID, to the to depot ID, and we can directly access the path stored in this vector of vector. Say if we do the find paths for all of the sources and we parallelize this for loop, will this code work? Yeah. And why not? Yeah, using pushback, first the order will get messy. And second, if the program is doing reallocation copying when they're doing pushback, and if it happens right at the middle where another thread is doing the same thing, it will get memory corruptions or lost data or something you don't want. So the right way to do this is to always resize the outer vector by the intersections and always store to the correct index. Every thread writes to a separate memory, so there's no reallocations and the order is not messing up. So in summary, debugging parallel programs, the first step is to disable parallelism and see if the problem disappears. If it disappears, then there probably is a race condition. So multiple threads are trying to write or read a shared variable or doing something weird. And the second step is to enable back the parallelism and run debugger. we can see all threads using the debugger tabs, and we can see the call stack for each. And see if they are trying to access a shared variable at the crash point. If they are, then probably there is a race condition on that shared variable. Fixing race conditions, the first step and the most common step is to privatize your variables to make them local variables so that each thread has its own copy. If this is not avoidable, you have to keep the variable public, or if it's not because of variable, it's because some resource being shared, like the output, like the print. Use OMP critical to force that only one thread can read, write, or do something at one time. This is not as good a solution because it costs performance, because it forces the threads to wait for other threads. But so only do this if it's absolutely necessary. Parallelization is limited even if you have infinite number of cores. And that's because we only have a fraction of work that is parallelizable. And that defines our upper limit for speedups. So you can get the maximum number of speedups you can get using Amdahl's law, which is this equation. So if you can only parallelize half of your work, so F is 0.5, 1/2. In this case, even if you have infinite cores, so that this term goes to 0, you are still limited by this term. So your maximum speedup you can get is 2x. Does this make sense? And that's why we are asking you to first do any speedups you can get by improving your algorithms before attempting to do parallelization, because the gain is limited and it's easy to parallelize after everything's done. So yeah, improve your algorithm first because it's usually a bigger reward. Add OpenMP pragmas to for loops, and this should be enough for your M4. And this is easily added and disabled. Avoid modifying shared state when you add the OpenMP parallel for. And this will minimize bugs. And try to privatize all of the variables, all the variables needed, so each thread has a copy and they are not interfering with each other. Only parallelize large chunks of work because creating threads has overhead. It is hard to choose to whether parallelize or not, or do parallelization. Even experts get it wrong, and it's still open research questions to know what and how to parallelize. So attempt this at the very end of milestone 4. Yeah, same thing as all of the suggestions we would suggest for all of the milestones. Get something simple working first. We want something simple to work for the travel time estimate, a simple ordering heuristic like greedy. Return a legal solution first. And then you can try to improve using better algorithms. And then parallelize only when everything is working well, and only if you want a further challenge. And it's a very short update, hopefully, for you. And yeah, that's the end of this tutorial. Any questions? Yep.
Because there is no front-end, but we are the same which that so maybe that is really like the office market and multiple number of things that we would like to identify the bigger and like
Yes, OpenMP will automatically determine the number of threads supported by your CPU, and that is 16 threads. But sometimes 8 threads can work better than 16 threads, but OpenMP only fixes on 16 threads. So if you want a further challenge, you can use the C++11 thread library, and using that, you can control precisely how many threads you want.
about the impact or factor. So I think we mentioned that it is not going to work because of like even though we are not caring about people, but because when we also take to the factor, but we all take that like the middle of it, like another than just looking back that
Yeah.
like there will be like the problem. So like the solve is it like it's the critical like the human solve
The critical?
that's one line that when you put that line like it was actually one that can take the first like that line
The OpenMP critical?
or
If you are not using pushback, you don't have to do that.
like we want to push back like drop that the only way.
If you want to do pushback, then yes. If you don't worry about the order, of course. If you don't want to worry about order, but you want to use pushback, you can use the critical, OpenMP critical. It might affect your performance by a bit.
That the fact that
That will avoid the memory corruption.
that is like serialized part of that.
Yes, that serializes that part.
Okay, so maybe like maybe like address here and then doing some hardware and then there's this line and only like that serializing like this line and the other part of them.
If you put that line in, then only one thread is allowed to do that line at once. So all of the other threads are idle and waiting for that thread to finish.
But the function, okay, so this is like a long, like this is like long thing. Like the fact about it.
Yeah.
Okay, so I assume that we are like pushing factor here, and then we are doing something else like before this. So does it mean that okay, with this line here, like the factor of it will be it's like long and then generate that thread can like push through.
Yeah. Yeah, if you want to separate all the blocks for critical section, first you'll have to add a bracket before the critical, the end of the block. So that will separate out that block section with everything else that you are parallelizing. And then all of the threads will do everything else parallelized, and when they reach that block, that line, yeah, they will
Like this,
wait for.
they would like go through the waiting.
Yeah, there will be a loop that only one thread can run to execute that line.
I think you mentioned like adding a bracket for the critical block.
Adding brackets. Yeah, adding brackets will define the blocks. that your compiler will understand. Like, it doesn't have to mean anything, but the compiler will understand that.
It's like it's the syntax, something like that. Like what is the
Yeah,
syntax?
the-
Oh, so it's like here and then like
something like this.
Yeah.
and then for other parts of this thread, it will be.
Yeah.
Yeah. But test before actually
Oh, yeah.
doing this, yeah, because I can't guarantee it.
Oh,
Yeah.
okay, yeah, thank you so much.
Yeah.
Nice.
Any other questions? Yeah.
Yeah. Yeah, it might be a Thursday. I'm thinking about, are we needed to like further implement our functions in M3?
So your functions in M3, it's just the cost, computing the cost,
Yeah,
and
so
then
it's,
the
yeah.
A star.
It's basically like that contra and A star to get the distance only between 2 points.
Yes, you will need to modify your Dijkstra so it does multi-destination.
Yeah. And do we need to use the A star? Because yeah, sorry.
Yeah, so the A star that I talked about at the beginning, like the K-squared approach,
Yeah, I thought
A
they're
star.
like even slower.
that's really slow.
Really?
So we do recommend that you stick with. If you have the multi-destination Dijkstra, use that. If you want to first test it and just get a simple solution, you can just call the same A star. Yeah, and do the K-squared approach.
Yeah, I'm just a bit confused because like why the A star is lower, because like for the lowering for the two point A star should be lower.
A star is not much faster. Like its speed up can be only like 1 point something x. So it's not really that faster compared to Dijkstra. And for the A star, between 2 points, it can be faster than Dijkstra. But in our case, we want to get the path between one source and all of the destinations. Then it's not really worth it to do A star anymore. If you can do multi-destination.
Yeah, thank you.
Yeah.
Yeah.
Oh, if no one else has questions, yeah, that's it. And thanks for coming.
I have a question about the travel salesman.
Yep.
So, do you have any like advice on how to make it fast?